when we talk about like diffusion, for example, molecules like to move down their concentration gradient, area of high to low, okay? Are we not going from high to low? Yes. So we have a pressure gradient, and the fluids like to flow down their pressure gradients because this does not require any energy. It's when the contraction occurs that we're going to require energy. And the heart demands a huge amount of energy. Those mitochondria in these cardiac cells making up this muscular tissue. Do you guys see now why I keep pointing out that this muscular tissue is around my ventricles? Because when I look at the structure of my atria and what the atria have to do, they don't need a lot of muscle. Okay? So, like I was showing in the picture, we start out, if we're looking at it based on a cycle, blood returns to our atria. When the atria are empty, pressure is low, but as it begins to fill, it puts the pressure on my valves. The valves will begin to open, and the flow of blood will begin to make it into my ventricles. From my ventricles, when the contraction occurs, they move into their great vessels, and we start the process all over again. Now, granted, it is a tad bit more difficult than that, okay? But for our purposes, that's what's happening. So now we're looking at having a pressure in the chambers themselves. But when we tend to think about pressure associated with the cardiovascular system, we tend to think of what can be taken as a measurement. That's because it's very difficult to get something mechanical into the chambers of the heart to check the pressures. Okay? I mean, I don't think I would like that. Okay? So, what we do is we take a pressure reading and we listen. All right? And one of the things that'll happen, if they're doing the pressure manually, they'll be listening. If it's done by the machine is hopefully working correctly and taking the readings. As the blood moves, so think about this for a second. In the structure that we have of the heart, I have my right and left atrioventricular valves, and then I have my semilunars. One going to the pulmonary circuit, one going to the aorta. As these open and close, open, close, open, close, open, close, open, close, open, close, they're making noise. So what we call it is turbulence. Everybody's familiar with that term, right? Okay? So when you're being taught how to listen with the stethoscope, which, you know, is auscultation, anytime you listen to something, you auscultate, okay? Because they can use that stethoscope to listen to the abdomen, the heart, the lungs, okay? So they're auscultating whatever it is they're listening to. For the heart, we have norm, two sounds. There is a third sound, but it's very rare over the age of 30. And in children, it may be present, but usually as they continue to grow, it's no issue. If it continues as we continue to get older, and it's very prominent when they're listening to the heart, they need to check on some other things that might be taking place. Usually indicative of an enlarged heart or a failing heart. But under the norm, we have the first and the second heart sounds, represented by S1 and S2. One is usually louder, and they say lupta. That's sort of how it sounds when you're listening to it. Lupta, lupta. Now, what it's doing is it's giving us the sounds based on these valves opening and closing. And they have a very unique sound that you hear. So, as these open and close, and as someone is listening, hopefully this is what they hear. The lupta, lupta, lupta. Anything else should let them know something is wrong and to check it further. That cardiac cycle that we keep mentioning, that one complete heartbeat, contraction, relaxation, okay? What this is doing, and as we listen, as we take pressures, hopefully describing to us what is happening during contraction, systole, and relaxation, diastole. What is taking place during these activities? What's taking place at the time of or in both atria, ventricles? Hopefully, we're going to get information about volume and pressure changes and the action of the heart valves. Anyone in here ever been told they have a heart murmur? Know anyone who has? Is it anything they have to pay a lot of attention to? Did they have to have it corrected?
I did clinicals when I was last year when I was a senior. So like I used to hear, like I have to listen to the heart and blood sounds. I used to hear like crackles or like the difference in their breathing in the heart.
For people that may have had it?
Mm-hmm.
Okay. And these are the things that you get taught, okay, as you move forward into the clinicals. You get to be taught what is the norm, so anything out of that norm, you know, should be checked a little further. Hopefully, all of these will be heard with the auscultation. And in your textbook, there's a lot of information in there, like the sounds, like giving you the love dub and all that sort of stuff. Just kind of read over that, be familiar with it. It's a lot of what we've talked about already with the flow of the blood through these valves. And as the blood flows through the heart, we have normal values that we look for. Now, these values, the values we're looking at right here are based on like a healthy 21-year-old. All right? Now, as ages change, okay, whether baby to child to teenager to adult to older adult to elderly, the values are going to change, okay? But what we want to be familiar with, all right, is something called cardiac output. Your textbook is going to get into great detail about a lot of this. It's going to start out with talking about this volume, that volume, doing this math, doing that. No. Okay? My goal, I want you to understand that Cardiac output is something you will see when you get out into the world of the clinicals and the job, because this lets us know the blood volumes. So what we're going to say, cardiac output equals what our heart rate is times the stroke volume, meaning the amount of blood. A typical resting value for cardiac output under normal conditions, we have about 75 beats per minute. In that heartbeat, there's about 70 milliliters of fluid. So if you think about that structure of the heart, okay, in a heartbeat, there should be about the 70 milliliters present. Now it's going to be a little more, a little less based on some other volumes that are present, okay, but under the norm, okay, for every heartbeat, that means for a minute's time, our heart is moving over 5,000 milliliters of fluid. 5,000 milliliters of fluid. Right there. For this amount is what is getting moved through our heart per minute at rest.
Oh, per minute. Oh.
That amount per minute at rest. Note, I'm stressing that. Okay? So, that tells us that our total volume of blood in the body at a given point in time is roughly 4 to 6 liters. That volume can change, and the body and the heart can adapt to it. Okay? So, that is the amount of blood. For example, actually, by the time the person would lose about 3 liters is when death would occur. Now, think about the cutting, for example, like if something happened and the severing of the femoral artery. This is why, if you don't get that femoral artery, contained, stomps that blood flow, this is why within just a very short amount of time, that person's dead. Because they have lost the majority of their blood volume. And it means their heart has nothing to pump. Now, a belly wound, for example, about 20 minutes time. You have about 20 minutes. But still, if the person bleeds out for that 20 minutes, chances are replacing that blood volume is going to be difficult. They're going to need to be given blood, all that sort of stuff. Do you see the importance of having this blood volume? Now, lots of things affect our blood volume. For example, our level of hydration. The better hydrated you are, the better that blood volume is. All right? But this, like I keep saying, it's not constant. It varies. Huh? What? How is it that 4 to 6 liters can go up to roughly 21